Hey, thanks for tuning in to Check This Out Mathematics. And I encourage you to like these videos and subscribe to the channel and leave some comments and watch more of the videos that have been posted. Okay, so in this series of videos, we have been talking about formulas that generate Pythagorean triples and the underlying concepts. And so specifically, we've been talking about these three formulas that generate Pythagorean triples. And we have a couple of videos posted about this first one here. And a couple of videos have posted about this second formula that generates Pythagorean triples. And we also have a couple videos posted about this third formula that generates Pythagorean triples. And so now we're going to do one more video about this last formula that generates Pythagorean triples. And in this video we're going to show how this formula came about. Because that was the actual one of the inspirations to make all of these videos that have been posted. Seeing how this formula came about. And so that formula, along with this illustration here that shows how all the Pythagorean triples, where the A, B, and C values are just one or two digits, or that is, they're all under 100, and you can arrange all of those particular Pythagorean triples in this nice 3, 4, 5 triangle arrangement. And so with the how this last generating formula came about here, and this illustration behind me, and of course some of the other mathematicians that have produced mathematic videos here, Weihart and Black Pen, Red Pen, and Numberphile. Those are also some of the inspirations that are behind these series of videos. So I just want to give a shout out to these these people that have made these videos also, and you can check them out on YouTube. Okay. All right. So in the video previous to this one, we showed how this formula that generates Pythagorean triples, if you substitute it in this expression for A, and this expression here for B, and you squared them and added them together, that you would in fact get this expression for C squared here. And so you can go back and check that out. But now we want to get into this idea of where did this, how did this this formula come about? And so, you know, if we do some things with the numbers that are involved, you know, that's what mathematicians do. They play around with numbers and see what happens, you know. And so let's, for instance, take this Pythagorean triple 8, 15, 17. Okay. So that's this one right here. And let's maybe do something with these numbers. Let's add the 8 and the 15 and subtract the 17. Why not? Okay, and so then 8 plus 15, that's 23, minus 17, and that's 6. And so we got this value 6 from going through this little series of operations here. And then maybe we could do something like, who knows, take the 8 and subtract the 6, and that would give us 2. And then let's also take the 15 and subtract the 6. Okay, so we take the 15 and subtract the 6, and that gives us 9. And so now, with this arrangement, we can do something kind of interesting here. We can take the first value, the 6, and the second value, the 2 here, and of course, if you see how we did the addition and subtraction, of course, this 6 plus 2 is going to equal to 8. And then if we take the 6 plus 9, we'll get the 15. And now this also works out where if we take the 6 plus the 2 plus the 9, then well, that gives us the 17. 6 plus 2 plus 9. And so that's 8 and 9. Oh yeah, that's 17. Okay, so Pythagorean triples can be written in this manner. Let's take another one. Let's do this one here. 20, 21, and 29. That's oh yeah, that's right. Okay. All right. So we take that Pythagorean triple there, and again we go through that addition and subtraction process where we say 20 plus 21 minus 29, and that's 41 minus 29, and let's see, that's going to be 1 for 30, that's going to be 12. Okay. All right, so now then that gives us our first value there. And so we can take that 20, and if we say 20 minus 12, that gives us 8. So now the 20 is going to be 12 plus 8. Okay, and then let's see, we'll take that 21 and subtract the 12, and that gives us the 9 here. Okay, so we did the 20, we arrived at this number by adding the A and the B value and subtracting the C value. So that's what we did here. We did A plus B minus C. And then we got this value 12 from that arrangement. And then we subtracted the 20 minus 12 to find the 8 there. And then we subtracted the 21 minus that value 12, and that gives us 9. So 9 plus 12 will be 21. Or let's write it the other way so we can have the 12 first. 12 plus 9 gives us the 21, and then if we add the 12 and the 8 and the 9 together, 12 plus 8 plus 9 together, we can see that. That's 12 and 8, that's 20, and 9 more, that's 29. Okay. So this arrangement is working for a way to express this Pythagorean triple. And so let's give these values some names. So this a plus b minus c is going to give us this value we'll call p. And then when we subtract the 20 minus that p-value, we get 8. And so let's call that the q value. Okay. All right. So then p and q, and then when we subtract the 21 minus the 12, that's going to give us this 9, and let's call that value r. And so now if we say this is p plus q, and then p plus r, and then this is p plus q plus r. P plus q, p plus r, and p plus q plus r. Okay, so we can write Pythagorean triples in this manner. And so the next thing we might wonder about is does this p plus q and p plus r and p plus q plus r, is that a solution to the Pythagorean theorem? Well, let's find out. Okay, that's what we do in these videos. We find things out, right? Okay. All right, so here we go. We're going to say we're wondering if a squared plus b squared equals c squared, the Pythagorean theorem here. We're wondering if we can take this arrangement, p plus q and p plus r and p plus q plus r. We're wondering if we can take this expression and show that it's a solution to the Pythagorean theorem. And so what we want to show is that p plus q squared plus p plus r squared, and we're going to put a equals with a question mark there, and whether that equals p plus q plus r squared. So the question is this p plus q for A and p plus r for B, will that be a solution to the Pythagorean theorem? And so let's go through that and see if that works. Okay, so let's do the first part here. P plus q squared plus p plus r squared. Okay, and we're going to do that by remembering this expansion, that whenever we have x plus y squared, that gives us x squared plus 2xy plus y squared, as we have used in previous videos. Okay, so that means p plus q squared will be p squared plus 2pq plus q squared And then p plus r squared will be p squared plus 2pr plus r squared. Okay, so when we expand the p plus q squared, we get p squared plus 2pq plus q squared. And when we expand the p plus r squared, we get p squared plus 2pr plus r squared. And we can combine a couple like terms here. We'll have 2p squared plus 2pq plus q squared plus 2pr plus r squared. Okay, so we can combine this p squared and this other p squared and have 2p squared. Okay, so that's the expansion of p plus q squared and p plus r squared. Okay, so now let's do the next part of this. That's the p plus q plus r squared. And so we're going to take p plus q plus r squared. And we're going to expand that. And we're going to do that by this idea here that we can write the p plus, we can think of the p plus q as the x. So then we have x plus y squared. And so using this same expansion here, we will say this is going to be p plus q squared, that's the x squared, plus 2x, which is p plus q, times y, which will be r, and then plus r squared. Okay, so we're thinking of the p plus q as our x and the r as our y. We have x squared plus 2xy plus y squared. Okay, now we already know that p plus q squared, well, we already did that before, but we'll write it out again here. P squared plus 2pq plus q squared. Okay, so applying that x plus y squared to just this portion here, we get that. And then if we run the 2r through the p plus q, so 2r times p is 2pr plus 2pr. And then 2r times q, that'll be 2qr plus 2qr plus r squared. Okay, now let's see, are there any like terms here? We have p squared plus 2pq, q squared, 2pr, 2q, no, there's no like terms. Okay, so let's look at these two slides here. And we're going to switch them around here. There we go. Okay, so we have over here on this slide here, we have p plus q squared and then p plus r squared. And that gives us 2p squared plus 2pq plus q squared plus 2pr plus r squared. And then over here for the p plus q plus r squared, we have a We have p squared plus 2pq plus q squared plus 2pr plus 2qr plus r squared. Okay, so now let's compare these. Well, if we look at we have a r squared in both of them. And I'm just going backwards through here. So, and then we have a 2pr in both of them. And we have a q squared in both of them. And we have a 2pq in both of them. And, well, let's see. So, if we cancel out these terms here, 2pr and 2pr and 2pq and 2pq and the q squared and the q squared, you know, and maybe that was, we had that 2p squared there. That's kind of what was throwing us off here. Maybe if we write that as just the p squared plus the p squared there. So going back here, this 2p squared is p squared plus p squared. Okay. And so if we, again, if we, have to switch them again. If we compare them, we were able to cancel out the 2pq and the q squared and the 2pr and the r squared, and now, and we can cancel out a p squared. So we have a p squared here and a p squared there. And so now let's circle what's left over. We have a p squared here and a 2qr there. Okay, so over here on this slide here, we were able to cancel out almost everything with this slide over here, and the two things that are remaining are the p squared over here and the 2qr over there. And so these two expansions are equal if p squared equals 2qr. So if p squared equals 2qr, then if those things are equal, then the two expressions are equal. Okay, so let's write that down. Trying to save all these slides in case I need them. Okay, so if p squared equals 2qr, then p plus q squared plus p plus r squared equals p plus q plus r squared. Okay, so this the expansions for this side, the left-hand side and the right-hand side, are equal to each other if p squared equals 2qr, as we just discussed. And so now then, so if we pick a p and a q and an r, well, then we ought to be able to generate a Pythagorean triple, as long as we have this true, that p squared plus 2qr is true here. And so if we go back to this earlier Pythagorean triple, let's see that that's true. And so let's take the p value and the q value and the r value. Let's take the p value and the q value and the r value and see that if we take p squared, so that would be 6 squared, and then we say 2qr, so then that's 2 times 2 times 9. And yeah, that's 36 equals 36. Okay, so this is kind of happening here. That this way of finding the... did I do that? Where's my slide? Oh yeah, here. If we take, this is our way of finding the p value, a plus b minus c, and then we can find the q value and the r value from that. And so this condition that we have here, that p squared must be equal to 2qr for this expansion to work. And so here was one of our choosings for p and q and r, and it fits that condition. And here was another way that we found p and q and r, and let's see if that's happening. So we have the p value, we have 20, 21, 29, and then we have 12 plus 8, and 12 plus 9, and 12 plus 8 plus 9. Okay. And so we want to see if that gives us that p squared equals 2qr. Okay. And so then that would be 12 squared equals to q2 plus 8 plus 9. And 12 times 12, that's 144. And then 2 times 8 is 16 times 9. So 16 times 9, well, that's 144 also. Okay, so it's happening on this Pythagorean triple also, that this condition is being met. And so now let's go through it one more time. This time we will we did the 8, 15, 17, and the 20, 21, 29. And so now what we want to do is this one. Okay, so let's say that if we choose that's with 2 O's, a p and a q and an r, where p squared equals 2qr. So let's choose a p and a q and an r. And for this problem, I'm going to choose, let p be 4 and q be 8 and r, hold on, q is going to be 1, and then r is going to be 8. Yes. Okay, so now, so we've chosen a p and a q and an r, and let's show that this fits the condition. So if we take 4 squared, that's 16, and if we do 2 times q, which is 1, times r, which is 8, that gives us 16 as well. Okay, so we have chosen a p and a q and an r that fits the condition that p squared, that's 4 squared, is equal to 2 times q times r, so that's true. And so now this these three values, when we add them together, in a certain way, then we should get the certain Pythagorean triple. Okay, and so let's do that here. We'll take the p value, which is 4, plus 1, which is the q value, and then we have 4 plus 8, which is the r value, and then we would have 4 plus 1 plus 8, and now we have the 5, 12, 13 Pythagorean triple. Okay, so we know that this is true, that p plus q squared equals plus p plus r squared equals p plus q plus r squared if p squared equals to 2qr. And we happen to choose 3 values, 4 and 1 and 8, where the p squared is equal to the 2qr. And that did, in fact, give us a Pythagorean triple there. So that's all we have to do for this, to get these Pythagorean triples, is choose a p and a q and r, where p squared plus p squared equals 2qr, and then if we add them in that manner, we will get a Pythagorean triple. So the thing is, we have to choose 3 numbers, a p and a q and an r value, and they have to meet a certain condition that p squared equals 2qr. And then if all that falls into place, we will get a Pythagorean triple. So, you know, it's a really nice idea. It's Dickson's method, and you can do some more looking at that. Okay, And so a certain mathematician thought of this idea, and it's really very good. I like it. But maybe we can do something with it. Maybe, because what's happening here is we have to choose a triplet of values to get a Pythagorean triple. You need 3 values to get 3 values. And those 3 values have to fit this certain condition. And so maybe there's a way to not have to pick 3 values. And in fact, just pick 2 values. Like this formula has 2 values, m and n. And this formula has just 2 values, s and t. And maybe we can remedy this this condition, p squared equals 2qr. Because when we were doing this one, this Pythagorean triple generating formula, the m value had to be greater than the n value. So there was a condition upon it. But it was nice, there was just 2 values that you needed, 2 values and a condition that m had to be greater than n. But the thing about this Pythagorean triple generating formula is that there's just 2 values and there's no conditions. So we're going to show how this Pythagorean triple generating formula came from this Dickson's method, which is here, and how we can maybe simplify it a bit. All right. So let's see how we can do that. So here's our condition that if p squared equals 2qr, then p plus q squared plus p plus r squared equals p plus q plus r squared. But maybe we could, again, simplify this where we don't need 3 values and we don't need the condition. We want to simplify it down to 2 values and no conditions. Okay, so let's my notes on this. Yeah, here it is. Okay. All right. So this is our condition that p squared equals 2s, equals 2qr. And so let's see if we can simplify this with 2 values. So let's choose an s value and a t value. And let's say that p equals 2st. Okay, so 2st is going to be in place of the p. And then let's have q equal to 2s squared. And let's have r be equal to t squared. And now check this out. See what happens here. So we'll put in 2st for the p. And square it. And that will give us 4s squared t squared. And then we can take the, we can have the 2, and then q will be 2s squared. So we'll have 2 times the q value, 2s squared, times the r value, t squared. So we have p squared, that's p is 2st, and we squared it, and we got 4s squared t squared. And then 2 for the condition here. And then q is 2s squared, and then r is t squared. And so now check this out. It's so beautiful. This gives us 4s squared t squared. Okay, so let's see. So we can now choose 2 values and not have any conditions on those 2 values, and they will fit the formula that we have here for generating Pythagorean triples. And so let's see. Okay, so we have p plus q. Well, let's see. I think we can write it down here on this side. So we'll let p equal to 2st and q equal to 2s squared, and then r be equal to t squared. Okay, that's what we had here in this slide here. And so now, instead of having p and q and r, 3 values to get a Pythagorean triple, and this condition has to be met, well, the condition is already inside of the problem with this s and this t value that has been chosen. It's already been integrated. That's a good word for math, right? Okay, so then we can say 2st plus 2s squared. That's the p plus the q. And then p plus r, that's going to be 2st plus t squared. And then p plus q plus r will be 2st plus 2s squared plus t squared. Okay. And so P is 2st, and Q is 2s squared, and T and R is T squared. And now we have a formula that generates Pythagorean triples. And all you have to do is choose two values, S and T, and arrange them in this fashion here, and you will generate Pythagorean triples. You will generate Pythagorean triples as we had showed in the previous video. And so that's how this formula came about. The idea that if we that this identity is true if p squared equals 2 plus p squared equals 2qr, and the desire to simplify it by writing it as two values that need to be chosen, s and t, and not having any conditions on this formula that generates Pythagorean triples. So yes, this is another formula that generates Pythagorean triples, and this is the simplification of that formula. Okay, and so that finding this formula that has that generates Pythagorean triples with no conditions and two values that need to be chosen, and this illustration here, and our esteemed other, did I keep that? Oh, there it is. Our esteemed other producers of mathematics videos, by heart, Black Pen, Red Pen, and Number File, all gave the inspiration for these 12 videos that are now been posted. So that's very exciting. I did what I set out to do. That's a good thing. Okay, thank you very much for tuning in to check this out in mathematics. And I encourage you to like and subscribe to the videos, subscribe to the channel, and make some comments and watch more videos. Watch these videos again and again and tell everybody about them, and then we'll be able to make more content and to show you how fun and interesting mathematics is. All right, Mr. O'Donnell signing off. Thank you.